Hello everyone, welcome to my channel and welcome to another physics lesson. I'm still looking at work, energy and power, and this is lesson 2. In lesson 1 I looked at one example, and in this one I want to look at example number 2. These examples are quite long and therefore I'm trusting that this one here will be sufficient for this video. Now example number 2 here, which is our question for today. A box of mass 180 kilograms is being dragged to the right on a rough horizontal surface by a force of 800 newtons at an angle of 30 degrees to the horizontal. The velocity of the box increases from 8 meters per second to 8.96 meters per second from A to B through a distance of 10 meters as shown in the diagram. So this block is being dragged to the right by a force of 800 newtons. At this point A, it has a speed of 8 meters per second, or velocity of 8 meters per second to the right, and it covers a distance of 10 meters, and at point B it has a velocity of 8.96 meters per second. The force remains 800 newtons at an angle of 30 degrees to the horizontal. Question 1, that's 2.1, says using energy principles determine work done by friction. Right. And then number 2.2 says prove that the coefficient of kinetic friction between A and B is 0.4. And B kinetic coefficient of kinetic friction is 0.4. We need to show that or prove that. So how do we go about this, right? So here is how we approach it. I'm going straight to page 2. You would notice that they are talking about friction in this question here, and we're supposed to use energy principles. And when the surface is rough and there's no collision that has taken place, the only approach we have is work energy theorem, because we're talking about energy principles here. So, and the surface is rough, it means that the system is not isolated. There's friction present, and therefore we have to use work energy theorem. So question number 2.1, we approach it as follows. The first thing we have to do is to draw a free body diagram. When you have a question like this, using energy principles, normally they are requiring you to use work energy theorem. We have to first of all identify what kind of forces do we have in this diagram. So free body diagram is the first approach or first step. And here is the free body diagram. We have a normal force acting vertically up, and we have frictional force, opposing motion, and obviously we have gravitational force, Fg, acting downwards, which we know is mass times gravitational acceleration. This is kinetic frictional force, Fk, and that's normal force, Fn. And we know there's an applied force in that direction. That force, let's just call it F. It is applied through an angle or at an angle of 30 degrees to the horizontal. So I'm going to, this is a free body diagram, by the way. It would be like this. But I want to include the components of this force, because it's the component of this force in the horizontal direction that we're interested in. So therefore, adding components of this F here, we have the horizontal component, and then we have the vertical component. So we're not interested in the vertical components. We're only interested in that force there, which is Fx, the component of this force in the horizontal direction. Remember, this is our angle theta, and theta equals 30 degrees. And in lesson 1, I did show you that this is exactly equal to F cosine of theta if you use trig ratio cosine in that right angle triangle. Now, we have two forces in the horizontal direction, this one and this one. And therefore, when we use work energy theorem, we're interested in work done by net force. So it will be the sum of these two forces, of course, with the choice of direction, which we make in this case as the choice of direction of motion of the object as our positive direction. So this block is moving to the right, and I'm choosing to the right as positive. Therefore, I'm gonna go straight to work energy theorem now, which basically says W net is equal to delta Ek. This is work energy theorem. Always start from here. And we have two forces here, so we are interested in work done by frictional force. Remember, the word net means sum. So work done by frictional force, let me just say Wf. In the first video, I said Fwk or Wfn, Fk, whatever symbol you want to use, as long as you know that this is work done by frictional force. Net means we are supposed to add and this is going to be plus work done by applied force. Let's just call it F, work done by applied force F. We know that it's a component of F that does work on the block in moving it from point A to point B. Now, this must be equal to, remember, delta EK is half M V final squared minus half M V initial squared. Now, let's put in what we know. This is half of what is mass, 180 kgs. What is final velocity? Well, in this diagram here, final velocity would be velocity at B, which is 8,96. So 8,96, we square it minus half of 180 again times the final velocity. Actually, initial, final velocity is 8,96. Our initial is 8. That's our initial. They are 8 at A. So we have to say 8 and we have to square this. Let's punch the whole of this into a calculator all at once. And we're basically saying 0.5 times 180, 0.5 times 180 times 8,96. We're squaring that, minus 0.5 times 180 times 8, and we're squaring that. The calculator says this is 1465, 344. We know that that's energy. So this is work done by frictional force plus work done by applied force, component of applied force. Let me just put WF there. Now, the question is asking us to work out, I'll come back and fix that. The question is asking us to work out work done by frictional force, this one. Therefore, for us to be able to work out this, we need that. And to work out that, we have to use the definition of work done, which is force times distance that the object moves in the direction of applied force. So this force is our applied force. So that means we are going to say WF, work done by frictional force, plus this work done by F applied force. It will be done by the horizontal component, Fx. So I'm going to say times plus Fx times delta x, and this should be equal to 1465, 344. Let me fix this part here. And I said this is just WF, work done by applied force. Right, now this one here equals that part. But remember, what is Fx? Fx is actually F cos theta. There it is. Taking us to page 3. So I'm now going to say, if I put it up here, and I'm going to move this one down so everybody is able to see this. Right, page 3. So we're now saying this implies work done by frictional force plus, what is Fx? Well, Fx is F cos of theta times delta x. And this is equal to 1465, 344. Now let's put in what we know. WF, work done by frictional force, plus F is 800 newtons. Here it is in the question, 800 newtons, and theta is 30 degrees. So we're now going to say 800 times cosine of 30 times delta x is the distance that the block moves in the direction of Fx, which is going to be 10 meters there. That's our delta x. Times 10 is equal to 1465, 3,344. 344. Right. Doesn't look very nice here. Let me just clean up a little bit. Let me remove this comma here. Yeah, 344. It can be seen from there, and I'll put a comma there in a few minutes. So this is work done by frictional force plus, let me compute this. So that's 800 times cosine of 30, and then times 10. My calculator says 6928,20323. So this is 6928,20323, and this is equal to 1465, 344. Now we can work out work done by frictional force. Now, therefore, work done by frictional force Let me put this comma here so that I don't forget. Right. So work done by frictional force, this has to subtract from that. Therefore, WF is going to be equal to 1465,344. We're going to say minus 6928,20,323. And our answer, let me put it here, work done by frictional force, which is what we're required to find, is actually this number, which is 1465.344 minus 6928.20,323. My answer is minus 5,462, let's say 86 joules to 2 decimal places. So that is work done by frictional force, and that's what the question required us to find. You saw in the first lesson that work done by frictional force is always negative. Why? Because frictional force opposes motion of an object, and that frictional force always acts parallel to the surface on which the object moves. So this makes a lot of sense. Question 1 has been answered. That's 2.1. We're required to use energy principles to determine work done by friction force or friction. So that is our answer. Now, number 2, take note of number 2. 2.2 says, prove, here it is, prove that the coefficient of kinetic friction between A and B is 0.4 between A and B. Now, for us to be able to work out coefficient of kinetic friction, we need frictional force. Remember the formula for work done by friction. Let me remind you here. We said frictional force Fk, this is kinetic frictional force, is always mu k times normal force. And I showed you in my lesson 1 on Newton's laws that as long as the object is being dragged like this at an angle, or just being dragged, this is actually equal to mu k. Our normal force is mg minus f sine theta. That's our normal force, and therefore Fk is equal to this. So this one here, we know mass, we know gravitational acceleration, we know applied force, and we know the angle. Our job is to determine this one here, frictional force. And so it is easy to work out frictional force because we know work done by friction. So 2.2, let me start from here. 2.2, I'm going to say WF, work done by friction, is going to be Fk times cosine of theta times delta x. Do I know this guy here? Yes, it's minus 5,462,86 is equal to, do I know of Fk? No, I want it. Cosine of, do I know the angle at which frictional force acts? Yes, if the direction of motion is that one, frictional force is always acting at 180 degrees to the direction, or from the direction of motion. That will be your Fk. So our theta in this case is going to be 180 degrees, and our delta x, as you saw here, is actually 10 meters. That's our delta x. So times 10. And so simplifying this, we have minus 5,462,86 is equal to Fk, which we don't know and we want it, times minus 1 and times 10. And this will be minus 10. So I have to divide by minus 10 both sides to make Fk subject to formula. Taking us to page 4, we can say here that let me move this one down. Right, this is good enough. Right, so we can now say on page 4 that we can say that Fk is going to be minus 5,462,86. We're dividing this by minus 10. From there you can see minus 10, and therefore Fk, remember that our target is not Fk. Our target is to show that the coefficient of kinetic friction is 0.4. So I'm not rounding off whatever I find here. Simplifying that, this will be 546,286. And we know that this is frictional force. It must be in newtons. Now I can say that Fk we know is equal to mu k, and then mg minus f sine theta. This is the case, you have a minus here when an object is being dragged at an angle of any angle, 0 or whatever, as long as the object is being dragged. This is the formula for a normal force. Remember, I told you that frictional force is mu k. It's kinetic frictional force equals coefficient of kinetic friction times normal force. And for an object which is being dragged, normal force is mg minus f sine of the angle between the applied force and the direction of motion. Now, let's put in what we know. So here, I'm going to put in 546, 286 is equal to, I don't know mu k, but I know m is 180, and I know g is 9,8, and I have minus, I know f is 800, a sine of, and I know theta is 30 degrees. So I have to compute the right hand side. So this is 546, 286 is equal to mu k times some number. Let's work that number out. So it's 180 times 9.8 minus 800 times sine of 30. And our answer is 1364. So this is 1364. And so we can work out the value of mu k from here. This means that mu k is going to be equal to 546, 286 all over 1364. Working this out on the calculator. Here we go. 546.286 divided that expression, that number, by 1364. My calculator says 0. You can see it here, 0.4005, and so on. That last part there is because numbers are being rounded off here, but otherwise our answer is 0.4, which is exactly what they wanted us to show. Now, these questions are nothing short of 6 marks and upwards, all the way up to maybe around 10 or so marks. So it's critical that you do practice physics and maths. We learn these two subjects by practicing statistics in that category as well, chemistry. You have to practice because mathematics can never be divorced from these disciplines. Right, if you're new to this channel, do not forget to subscribe. Your support is greatly valued. I'm going to stop here in this video, and obviously I'll come back with lesson 3, where I'll look at the inclined plane, because I want to talk about work energy theorem on an inclined plane, but I realize that should be covered in Newton's laws too. So I'll bring up that lesson before we can come back to work energy and power again and talk about the inclined plane, and then I'm going to move on to talk about what we call conservative and non-conservative forces, as well as power itself. All right, God bless. I'll see you next time.